Alright, so in this final video, let's apply the 4 methods we learned to a practical example. So in this exercise, we are going to consider a 3-story building where the mass and stiffness matrices have already been defined, as you see here. And for this building, we have 3 tasks. The first is to find mass and stiffness proportional damping matrices where the first mode damping ratio is defined to be 5%. The second task is to find a Rayleigh damping matrix where the first and second mode are fixed at 5% damping. And the final task is to use superposition where all 3 modes are fixed at 5% damping. So let's start with part 1. The first step, of course, is to calculate natural frequencies and mode shapes, as we will need them for the damping calculation. So this is done in the same exact way as we did in the previous unit, simply by solving the eigenvalue problem. So in this case, I'll just use MATLAB eig command to solve for these two. I've provided a MATLAB code that goes through this entire example, so I encourage you to follow through that code as we work through these. After plugging in the values of k and m to the eig command, I get the following natural frequencies and the following mode shapes. These are mass normalized, by the way. And so now we can move into finding the mass proportional damping matrix. To do that, we simply take the equation for A0 that we derived in the previous video, and we plug in all our information for mode 1. So the value for zeta 1 was specified in the problem. That's what we want it to be, 0.05 or 5%. The first natural frequency was 11.7, and so we get a final value of A0 of 1.17. Then simply we multiply our mass matrix to get the following stiffness matrix. So that's it for mass proportional. Similar approach for stiffness proportional. Now we use the relationship for A1 to get the following. And again, we multiply that value by our stiffness matrix to get the following value for the damping matrix. Notice how we used only the value for omega 1 in this case. Now moving on to Rayleigh damping. In this case, we'll need to use the values both for omega 1 and omega 2. Let's set up our main relationship first. Then we set up our system of equations. To solve this, we'll need to invert the matrix with the omegas in it. Let's call this matrix W. And so we have, after evaluating that expression, we get the values for A0 and A1. And plugging all that into our original equation, we get C equal to the following. Notice 2 things. First of all, our values for A0 and A1 are not the same as in the mass and stiffness proportional cases. And the C matrix is symmetric since both mass and stiffness matrices are symmetric. Finally, let's look at the superposition case. In this case, we'll be using all the modal parameters, both natural frequencies and mode shapes. Let's start from our general equation for CI. Notice that we'll need the values for the modal matrix, but since my mode shapes are mass orthogonal, these values are all going to be 1. But in a general case, you'll still need to define that, so let's go ahead and do that. Once we have those values, we can go ahead and calculate each corresponding C. Once that's established, we can use the inverse relationship to find our physical damping matrix. And there is your final solution. Note that your Mode shapes are not unique. They'll depend on how you normalize them. Therefore, your modal mass matrix, big M, is also not unique. And therefore, your modal damping matrix that you'll obtain is also not unique. But after you do the inverse, you will always get the same physical damping matrix. So C will be the same regardless of what type of mode shape normalization you choose to use. Note that the C in this case is very different from anything else that we derived using the other methods. All right, so go ahead and make sure you know how to implement this both by hand and in the code, and I'll see you next time.